So we're letting x, y, z, w be normally distributed with mean 0, variance 1, all i.i.d. Now, in part A of this question, we are asked to find an expression for this expectation of the CDF of the normal, but observe that we're putting in the normal random variable itself into it, and then we're taking the exponential, sorry, of this variable. We are then asked to leave it as an unsimplified integral. And so here we're just going to then write down the definition of the expectation as in the following way. Going to use lotus here, which means that we can take the PDF of z, so we don't have to find the PDF of this expression. We can just take the PDF of z and multiply that by this expression. That's what lotus is allowing us to do. Alright, so z, we know, goes over the whole real line, and now we can take the realized value z, so this is little z, and then the little z up here, and then we write down the PDF. So we can take the PDF. I'm going to write the PDF of z. It's getting a little ugly, like this and like that. Okay, so, and that is basically what we're asked to do. We can unpack this if we wanted to in the following way, just to give you that as well. Right, and then we take, so it's that's a 2 in there. This is then minus square 2 over z. So that's what lotus allows us to do here, is that we can just use the PDF of z. All right, now we're asked to find the expectation of this expression and then that expression. I was reading this first as, having to sort of move from here to these two, but nothing in the question actually implies that we should just treat them as two separate expressions. Obviously, we cannot use independence here because this expression here is not independent of this expression there. So it was a little confusing at first, but nevertheless, this is just a matter of treating them as separate terms. Okay, so what does this then mean, this expression? Well, using the universality of the uniform, so we realize that when you put any random variable back into its CDF, it becomes this whole expression here. Let's see, this in a term here becomes equivalent to a uniform random variable from 0 to 1. Okay, and from here on, then we can replace this inner term with u, and now we're left to solve a rather simple integral by just stating basically that we have little u here, and then the PDF of u is just 1, and then we integrate over this u variable. This gives us just simple algebraic manipulation at the moment in terms of finding the integral, and then this turns into half. All right, so that's the expected value of this expression here. And notice that, you know, actually doesn't matter what you put in here, as long as it transforms to the uniform 0, 1, it will always be half. Let's move on to solve the other one here, the other expression, e to the expectation over e to the z. Okay, so that one is the following, and here I was working with different ways of solving this, and one is involving using the MGF, and the other one not using the MGF, just like heading straight towards the solution, because it looks like, you know, this looks fairly easy here. I mean, you know, I was treating this as, you know, using Lotus again, you basically, and you know, I was not realizing this at first, but this is a log normally distributed variable. So, but then, you know, assume that you didn't realize it, you were just giving this. Then by Lotus, we can again just integrate, take the expectation over z, like that, and then we can let's see, just we can move out. Let's use the following thing here. We move out 1 to pi, and here we use the law of exponents like this, right? And now we would try to move this in terms of completing the square. Let's complete the square, and usually for me it's a little hard to see this just at once. So what I usually do is that I actually draw a square, and then trying to figure out what's going on. I mean, I'll be doing something like this, where you have, well, I forgot to do, there's a 2 here, so let's move this expression. We have minus z2 plus z. That would be a tend to try to just clean off the first expression here, so let's call this z, and then we have a minus 2z, right? When you multiply in the minus 2 and minus half, you get this expression back. And this little thing here inside means basically that we have a square that is z by z, like that. But we're now removing a portion of the square. Just trying to make it symmetric. Something like this. We're removing 2z. So what does that mean? Well, this means removing z 1 times z. So let's draw that. So imagine this being 1 of the size 1, then z length, right? And then we have another similar thing here, which is also 1. This is z. Now we have to find this piece here that completes the square, and this piece is 1. Well, this was a little too thick, so let me move this pen 1 by 1. So this is what we need to add back to this expression. So let's do that. Let's add plus 1 minus 1. Okay, and by that we have completed the square, so we are left with minus half, z minus 1 squared, and then there's a minus 1 in there. And that simplifies to minus a half, z minus 1 plus a half. Okay, so that's what's going on in the exponent here, so we can change this for that. Okay, so let's do it. Pi infinity minus infinity e to the minus half z minus 1 squared, and there's a plus half left dz. Going to continue down here. Just jumping here. Let's move this a little bit to the side to give us more space. Right, so what do we do here next? Well, this looks still a little complicated, but we can get rid of this little term to try to make this whole expression similar to what a PDF normal looks like. So let's get rid of that. That's e to the half, right? And taking, then let's right, so what we can do now is that we can move in this whole term in here inside the integral just to make it resemble exactly the distribution of a normal, a PDF of a normal. E to the z minus 1, 2, should be a 2, sorry, here looks awfully similar to 2, and here this is now exactly the PDF. This looks identical to the PDF of something looks like normal mean 1, variance 1. Right, the mean one is coming from this one here, right? And so with that, this whole integral integrates to 1. So we're now left with e to the 1/2 times 1, which is obviously just e to the half. And that is the value of this expectation here. Now, there's another way to do this, which is using the MGF of the log normal. Well, actually, it's the MGF of, because the MGF of log normal doesn't exist, because it integrates to infinity, it diverges. But if you use the if you start with the MGF of the normal, then there are resemblance, and you'll see some patterns there that gives you this value of a half. Okay, so we could let's show that. That would be fun to show. So let's start again from the beginning. So imagine, let's just copy this and say that you took another route where you saw this pattern of perhaps using the MGF. So this is just not using any MGF at all, right? We just went from this lotus and then basically algebraic manipulation down to this e half. Another way is then to recognize that this is actually a log normal, and then recognize that you can move through the path of an MGF. So let me state a couple of definitions here. So we know that Z is in Gaussian. Let's just put Y to be e to the z. Okay, and so this is now log normal distributed as before. Nothing else has been done here. Let me then start by saying, okay, so we want the MGF of let's see. Well, we'll just start with want the expectation of y to the n, and now we're going to say that the nth moment of this log normal, is equivalent to the nth moment of the of v to the z. Okay, so let's just write down what this means by definition. Let me just move this. I'm just keeping on moving this around. Just give me some little space here. So use now the definition of the MGF, e to the t to the y. Right, so there's one thing we should be clear about, which is that sorry, I just realized that this should be z. So this is the resemblance that we are talking about, this equality here. Okay, so let me move this around here. Let's again kicking it around. This is now the same thing as the MGF of z of t, and I'm putting obviously n equals t here. I'm using t because that's what we tend to use for the MGF, and now that is the same thing as what I just wrote here, but with a t, right? This is it, but there's a t in here. We're going to see that this t is now will be evaluated to 1. When we set it to 1, it will be exactly the same as the nth moment, which is 1 again, because that's what we're looking for, right? We want to solve this nth moment for the e to the z. Okay, so there was some jumping around here, but let's just write down now the definition of this thing in terms of an integral using Lotus. Again, this is e to the t to the z. Now we're basically back to the same problem as we solved, but now we have a t in there as well. So this is e to the z squared to the z. Okay, now let's move this. Now we complete the square again, but now we have a t in here. I'm not going to do that exactly, but you can just follow the same logic as I showed in the previous expression. So what I'm going to do is that I'm going to tell you what this is directly. So this thing, after completing the square, we get e to the, so there's a minus z minus t 2, there's a 2 in here, and then there will be plus 2 squared, like that. Okay, this looks a little ugly. I'm going to move it here. And right, and this is actually after removing this as well, right? Because that's what we did. We moved up this piece up here. We completed the square. We're left with this expression. Now we're going to move this out again, which yields e to the t2 like that, right? And this inner term in here is just this integral that is this piece in here, like this. And now this whole integral is distributed t1. Well, sorry, the whole expression here is the PDF of this distribution here, which then is 1. Okay, so this whole thing will be equal to 1, and that leaves us with the expression e to the t2 divided by 2. But we just said that because we want the first moment of the nth moment, which is 1, then because n is 1, t should be 1. So just going to say by implication, when t is equal 1, this first moment evaluates to e to the half. And that is the second way of solving this problem.